Welcome everyone to the second day of our first virtual meeting of the Simon's collaboration on special homology and geometry analysis and physics. And we're very pleased to have Andy Neitzke, who's going to give us an update on metrics on moduli of Higgs bundles. And just before we start, I want to say you've all been muted. If you want to ask a question, please just unmute yourself or place a question in the chat, whether you're on YouTube or here on Zoom. All right, go ahead, Andy.
All right, I want to thank the organizers for the opportunity to speak here. So I'm giving an update on what we understand about sort of explicit information about the hyperkähler metrics on moduli spaces of Higgs bundles. So the plan is roughly in 3 parts. So in the first part, I'm going to describe a rather general conjectural construction of hyperkähler metrics. And I'm calling it the Riemann-Hilbert construction RH because it goes by solving a certain Riemann-Hilbert problem. So as I say, that's a rather general construction which can be applied to all kinds of complex integrable systems. But then mainly I'm going to focus on a particular example, which is somehow the first paradigmatic example, which is the case of moduli spaces of Higgs bundles. And so I'll describe that example in part 2. And then in part 3, I'll describe what's the evidence that this conjectural construction actually works in the particular case of the moduli space of Higgs bundles, and what kind of information we get from applying the construction in this case. So that's the plan. Okay, so first thing, I should explain this Riemann-Hilbert construction. Maybe explain is a little optimistic. I'm going to describe the main features of this construction, but I'm not going to explain everything about it. So this construction originates in my joint work with Davide Gaiotto and Greg Moore, but it uses ideas from many people before that. So in particular, it has a lot to do with the idea of wall crossing of DT invariance. It was studied by Kinsevich, Soibelman, and Joyce. It also has to do with constructions of mirror manifolds pioneered by Gross-Siebert. It has a lot to do, in the particular case of, in many special cases, it has to do with cluster coordinates as studied by Fakh-Goncharov. It has to do with the twistor construction of hyperkähler spaces pioneered by HKLR, Hitching, Karlid, Lindstrom, Rocek, and work with many other people that I can't describe. Okay, so this is some construction. So I should tell you what are the inputs and what are the outputs. So there are basically 2 inputs. So input A is a complex integrable system. So I'll explain what I mean by that. I mean, it's roughly a particular kind of holomorphic symplectic manifold. And the point is, it's holomorphic symplectic, but not hyperkähler. It only comes to us with a holomorphic symplectic form. And maybe you think for some abstract reason, if you had enough compactness, being holomorphic symplectic would already make it hyperkähler. Here, we're interested in kind of non-compact cases, maybe where that general theorem doesn't necessarily apply. In any case, our goal is to give a somewhat explicit construction of the metric rather than a kind of abstract existence thing. So we'll start with the holomorphic symplectic data, and the goal is to make the actual hyperkähler object. Okay, so what do I mean by a complex integrable system? So as I said, it's a holomorphic symplectic space. So in particular, it's something of even complex dimension, but of a particular kind. So it comes fibered over a base of half the dimension, complex base of half the dimension. And the fibers, so I'll call a generic point of that base U. And so the fiber over U, if I call it pi inverse of U, so the fibers are Lagrangian, holomorphic Lagrangian. And what the generic fiber will look like is actually a compact complex torus of whatever dimension. So I'll draw the picture in the simplest kind of baby case. where the complex dimension of the base is 1, and the complex dimension of the fiber is 1. That's partly because that's the only case where I could actually draw the picture, but also in the very end of this talk, I'm going to present some kind of explicit results in an example, and that example will literally be of this kind. It'll be a one-dimensional base. Okay, so here's the base, and the generic fiber of this thing is a torus, literally a compact complex torus, and then there's some discriminant locus, which I'll call delta, and the fibers over there are some kind of degenerations of tori, and depending exactly how you set it up, those degenerations might look different. But the simplest case, which is good to have in mind, is literally the case of like a nodal torus. So it literally kind of pinches at a particular place. Okay, and let me write B prime for the base minus the discriminant locus, the kind of good locus. So my bases will typically be simply connected, but of course, once I take out this discriminant locus, it's not simply connected anymore. So that's the first input, is this complex integrable system. We'd like to construct a hyperkähler metric on, actually not exactly this space, it'll be on the dual of this space, so sort of replace every torus by its dual. You can roughly just ignore that and think that's basically on this space. To do it, we need one more ingredient. And that ingredient is, well, that ingredient is a bunch of integers, but organized in a specific way. So I'll call them DT type invariants, or maybe I should also call them BPS invariants, because they come from counting BPS states in physics. What are they concretely? So it's a bunch of integers. To even describe what the integers are, I have to first tell you what they depend on. So if I have a complex integrable system, then I have in particular a kind of local system of lattices that goes along with it by taking the homology, the first homology of the fibers. Here, actually, I want to extend that a little bit. Instead of just taking the first homology of the fibers, I want to take relative homology. I want to keep track of homology classes of two chains that end on the fibers. So that'll be a local system of lattices, local system gamma of lattices. So it'll be a local system over B prime, so like over the complement of these 2 points in this picture. And so because of that, it can have monodromy when you go around those points, where the fiber over a given point is the relative homology H2 of M check relative to the fiber. So of course it has a boundary map which maps it to H1 of the fiber. And actually you won't lose too much just by thinking of it as being H1 of the fiber. Okay, so that's just local system of lattices. I didn't tell you about the DT invariants yet. So the DT invariants or BPS invariants are a bunch of integers. So it's going to be an integer valued function. Well, I guess for each one of these lattices, we get an integer valued function, which absolutely not a homomorphism, by the way. It's literally just a bunch of integers, one integer for each lattice vector. And then as we vary the base point u, this becomes a, if you like, just a function on the total space of this whole local system. So that way I'll write it just omega from gamma to z, not gamma u. It's just a function on the total space of the whole local system. Now, if it were continuous, of course, it would just be locally constant.
Andy, could I ask a question?
Yeah.
Yeah. So when we thought about this, gamma u is just the first homology. Why are you using the relative homology?
It was the first homology of the spectral curve. Now I'm describing it in terms of the directly in terms of the integrable system.
Yeah.
So the H2, this H2 thing is the flavor part. You know, so H1 is the gauge lattice, and the extension is to include the flavor charges.
Okay, good.
Sorry, every time I do this, I present it a different way. So, anyways, okay, so we're going to give a bunch of integers, which are actually not continuous. So they'll behave in kind of a piecewise continuous, meaning piecewise constant fashion. And then as you move around, there'll be some critical places. As you move around in the base of the integral system, there'll be some critical places where these integers jump, and those jumps are not arbitrary, they're somehow constrained. And so there's a condition that the jumps have to obey, and that condition is called the Konsevich-Soibelman wall crossing formula. But I'm not going to explain the Konsevich-Soibelman wall crossing formula. I'm just telling you that there's some jumping behavior. Later, when I present an example, I'll just tell you what these integers are, and then it's just the fact that they obey this condition. But in the abstract setup, I'm just telling you there's some condition. And you can look in the papers to see what the condition is, if you want to. So that's one condition they have to obey. And the other condition they have to obey is some local conditions around the discriminant locus. So if you just impose condition 1, that would be one consistent thing would just be to have all the invariants be 0. That's consistent with the Konsevich-Soibelman wall crossing formula. If we do that, we'll get a perfectly good hyperkähler metric actually, but it won't extend over the discriminant locus. To make it extend over the discriminant locus, we have to impose some local conditions at the discriminant locus. Maybe I'll just say the very simplest example of what such a local condition is like. So if we look at sort of the most generic part of the discriminant locus, I'll call it delta naught of delta. The most generic part, the situation you have is you have exactly one kind of vanishing cycle. Like you can see the vanishing cycle in this picture. It corresponds to the cycle of the torus that is pinching off. So there's one vanishing cycle, which I'll call gamma naught, in a neighborhood of the generic part of the discriminant locus. And then the condition you impose is that the omega for that vanishing cycle, or multiples of that vanishing cycle, should be 1 for plus or minus the vanishing cycle, and 0 otherwise for all the other multiples. So in particular, you don't allow it to be 0, just identically 0. You have to have some non-zero invariants, and they're specifically controlled for the vanishing cycles. Okay, so anyway, the datum that we're gonna use is this bunch of integers that are defined kind of over the base of this local system and transform in some specific way as you move around. Now, just as a remark, in many examples, maybe always, these integers are actually determined by these conditions. So in that sense, you might say that they're not actually extra data. But in the construction, as I'm going to describe it, I'll just think of them as being extra data. Okay, so yeah, and there's one more. Okay, there's one more piece of data which we could include, so-called B field. So that'll be a class in H11 of check, whose integral over the fiber is 0. Greg, this is the flavor holonomials. So we could add such a thing, but I'm not going to, so I'll just take B equals 0 for the rest of the talk. That'll make my notation a little easier. Okay. Okay, so just to recap, so far the data is a complex integrable system, a bunch of integers that vary as I move around on the base of the integrable system in a specific way, and a B field, which I'll just take to be 0. And from that data, we're supposed to make a hyperkähler metric. Okay. Okay, so those are the inputs, and now the output. So the output is, well, let's say the output is a recipe for a hyperkähler metric. Which I'll call GRH, RH for Riemann-Hilbert. So as I said, strictly speaking, it's not literally on the M check, it's M, which I'll call the SYZ mirror to M check. And what that roughly means is it's kind of the fiber-wise dual. So I'll replace each torus fiber by its dual torus. Now, how are we going to construct this hyperkähler metric? So the strategy is to use the so-called twistor description of hyperkähler space. So here's a fact due to Hitching or Hitching, Carlin, Lindstrom, Rocek. A hyperkähler space, giving a hyperkähler space is equivalent to giving some more complicated set of data, more complicated sounding data. The key thing is this gadget called the twistor space. The twistor space is a space Z which is diffeomorphic to M cross CP1. And the CP1 coordinate I'll parameterize by a coordinate I'll call Zeta. That's kind of the inhomogeneous coordinate on CP1. But equipped with a bunch of structures. So first of all, it's a complex manifold. So it's a complex structure such that the projection to CP1 is holomorphic. So you can think of it as being like, yeah, I should say that. Projection to CP1 is holomorphic. So because of that, each fiber has a complex structure. And on the other hand, each fiber is diffeomorphic to M. So the way you're supposed to think of it is that M carries this CP1 family of complex structures. And if you started with, whatever is your favorite definition of hyperkähler, usually you say, oh, it has 3 complex structures that obey the quaternion relations. Well, once you have 3, you can easily, just by thinking linear combinations of them, make this 2-sphere worth of them. And that's the 2-sphere that we're talking about here. But the cool, kind of important thing that's maybe not 100% obvious is that those structures themselves vary holomorphically. In other words, if you think of it as a 2-sphere, and if you just think of it as a 2-sphere, you might not notice that the 2-sphere is actually CP1. And all these individual complex structures fit together into a complex structure on the total space. Okay, but anyway, that's true, and it's a kind of useful way of thinking about these spaces. So it's equipped with a complex structure. It's also supposed to be equipped with a fiber-wise holomorphic symplectic structure. I'll say O2 twisted for those who know. So roughly speaking, each fiber gets a holomorphic symplectic structure. But if you literally try to write a holomorphic symplectic form on each fiber, you won't quite succeed. You have to allow it to have poles somewhere. So you say it's O2. What you have is globally a holomorphic symplectic structure twisted by the line bundle O2 on the base. Anyway, roughly speaking, you have a family of holomorphic symplectic structures. And then the last thing you have to have is a real structure, which covers the kind of antipodal involution. Zeta goes to -1 over zeta bar on CP1. So that means in particular that if you look at 2 antipodal points, those 2 complex structures are opposite to each other always because of this real structure. Okay, so roughly speaking, that's the theorem of HKLR, is that hyperkähler space is literally equivalent to the data of the twistor space. Now, from what I said, I kind of roughly told you how to go from the hyperkähler space to the twistor space. But in fact, you can also do the reverse. If you only have the twistor space thought of as a complex space with all these structures, you actually reconstruct the hyperkähler space with its hyperkähler metric. And so when I say there's a construction of hyperkähler metrics, what I'm literally going to tell you is a construction of these twistor spaces. Well, what I'm going to sketch for you is construction of the twistor spaces. So how do you do it? So as a C infinity space, it's just M times CP1, right? So the tricky thing is to equip it with all of these structures. And so the way that we'll do it, is to give a recipe for constructing local coordinates, literally local holomorphic coordinates, and they'll even be Darboux coordinates. So they'll produce for us this holomorphic symplectic structure.
Andy, I think Claude Lebrun is pointing out something about the normal bundles of the P1.
Yeah. I didn't want to say that. So that'll happen automatically in this construction. So it's true. What I wrote is not. I'm missing some fine point, which Claude has mentioned. Indeed, not quite every Z will do. Yeah, I guess I should just say it. So right. So the point is, the way I presented it here, it comes with some distinguished sections, right? Which you get by just choosing a point of M. That gives you a section of this projection. That's going to be a holomorphic section of the projection. And yeah, you need some condition on what the normal bundle of the image of that section is. So that's like a CP1 sitting inside of the twistor space, and this normal bundle has to be a direct sum of a bunch of copies of O1. But so indeed, this construction is engineered to produce a thing which has that property. Okay, so the way the construction goes, we're supposed to give local holomorphic Darboux coordinates. So I'll call them little x sub gamma, and gamma is an element of this local system of lattices. So they're kind of indexed by the lattice vectors. They'll be on M times CP1, and the way you give them, unfortunately, you don't exactly give a formula. What you do is you give them as solutions of some system of integral equations. So let me write those equations. So here I'm holding fixed everything but zeta. So I pick a particular point of M. And now I'm going to write an equation for a function of zeta. So here's the equation. So first there's an explicit part, zeta inverse times z gamma. I'll tell you what z gamma is. Plus I theta gamma plus zeta z bar gamma. Let me tell you now what those things are, I guess. So z gamma is just some complex number which you get from the complex integral system by integrating its holomorphic symplectic form. So gamma, remember, was like some relative homology class. So think of it like some disk, and you're integrating the holomorphic symplectic form over that disk. That gives you a complex number. The theta gamma are the coordinates on the torus fiber of M. So remember, I told you M is like the dual of M check. So it has some torus fibers, which I'll just parameterize by coordinates theta gamma. If you like, you can think of theta gamma as being like the holonomias of a local system that you define on the original torus. That's how the SYZ picture would lead you to think of these theta gammas. Okay, so far so good. So far this is just a perfectly explicit formula, but the thing is I'm not done. So now I have to write one more term. And this is the term that involves those DT invariants, DT type invariants. So it's a sum over the whole lattice weighed by this number omega mu. So particularly if it's 0, you can forget this. The intersection pairing between gamma and mu. And now an integral, I'm a little worried that I haven't left myself quite enough room for this integral. So let me move over a little bit. Maybe now I have enough room. Integral over zeta prime lying in r minus z mu. So it's going to be integral over some ray in the zeta coordinate with some explicit kernel, zeta prime plus zeta over zeta prime minus zeta. And now the tricky part is there appears the log of 1 plus e to the x mu of zeta prime. So because of, so now you see, right, the x's appear both on the left side and the right side of this equation. And so for that reason, this is not just a formula for the x's. This is an integral equation which has to be solved.
So Andy, Greg Moore is asking about the radius r.
Oh yeah, so I just set it to 1 in this.
But really, there's a family of hyperkähler metrics.
There's a family of hyperkähler metrics, but I could reach that family just by rescaling this holomorphic symplectic form on the original complex integrable system.
And the other thing, in the log, it's 1 plus or minus, right?
Oh yeah, there's this sign that's always a pain. Sorry, you're right. Yeah, there's a 1 plus or minus, and I don't want to try to explain how you select that sign. Sorry about that. In the example I'll show you later, so I'll show you an explicit example later, and in that example, the sign will be plus, and that'll be the end of it. Good. Okay, so the game is you're supposed to solve this integral equation. Now, let's be optimistic for a minute and just assume that the solution exists. We'll talk later about, to what extent is it reasonable. Suppose that they exist. Well, right away, one comment about it is that that these x gamma of zetas obeying this equation would be not smooth functions, but piecewise smooth. Considered as functions on, well, as I wrote it, it's a function of zeta, but now I fixed the point of m. So I could also vary the point of m. And so then what these are is these are like functions on the twistor space. But they're not smooth functions on the twistor space, they're piecewise smooth. They have jumps. They have jumps at some codimension 1 walls. And the jump comes from the fact that if you look at this integral, the integrand has a pole in it. And so sometimes when you, as you vary all your parameters, sometimes the contour of integration will sweep across that pole. And at that moment, the function has to jump. So a typical kind of cartoon picture in the very simplest, I guess it's not typical, this is the very simplest example. You might have some picture like this. So this is a picture of the walls projected to the base. And they go through the discriminant locus, and then when they cross each other, they can kind of generate new walls like this. So there's some kind of wall and chamber structure like this. And so the idea is that this space that we're constructing, its twistor family is going to be built from, if you like, it's sort of built from simple pieces glued together along these walls. Okay. But if they exist, solving this integral equation, so as I said, we'll use them as holomorphic Darboux coordinates on Z. Then we get a twistor space with all the structures that it's supposed to have. And so we get a hyperkähler metric on M. That's how the construction is supposed to work. Now, you might ask, okay, what does that tell you about the hyperkähler metric? So of course, if you're able to solve this equation, then it tells you everything about the hyperkähler metric. If you're not able to solve this equation, what does it tell you? Well, one thing it tells you is just about the asymptotics. So roughly what happens in this business is that this integral term that I'm writing looks very complicated, but it has the property that it becomes smaller and smaller as these z's get bigger and bigger. So because of that, you can write down relatively easily an asymptotic formula for what the metric is like. It looks like this. So sorry, this hyperkähler metric I want to call G Riemann-Hilbert. G Riemann-Hilbert. So it has some simple form GSF plus corrections which are exponentially suppressed. Let me say what I mean. So first of all, what's this GSF? So this GSF is a sort of simple hyperkähler metric which you can easily write down if you only have the complex integral system. And it is the property that it's just literally flat on the torus fibers. In fact, I'll write down a formula for the Kähler form just to give some idea what it looks like. You take these functions z and z bar, the periods of the holomorphic symplectic form, and pair them using the intersection pairing. Take 1/2 of that and subtract some simple flat 2 form on the fibers. That's the Kähler form in the complex structure Z equals 0. So that's some very simple explicit formula. What does that metric look like? So concretely, if I go back up to my cartoon picture of what this integrable system looks like, this is a metric where literally each of those tori is just an absolutely flat tori with translation invariance. You can make a perfectly good hyperkähler metric like that it's called the semi-flat metric after, I guess, Gross and Wilson, who wrote down a similar kind of metric, thinking of it as an approximate metric on a K3 surface. Here we're writing the very same kind of ansatz, not for K3, but for this, well, for whatever complex integral system we're studying. Now, if you look at that metric, so it's perfectly translation invariant on the torus fibers. And one thing you realize about that is it can't possibly extend over the whole space. Why can't it extend? Because when you look at the when you look at the degenerate fiber, you see that the degenerate fiber is supposed to be pinched off, literally pinched off at a particular spot. So when you go very close to that, the thing has to be very inhomogeneous in order that it's going to pinch off in this particular place. The semi-flat metric doesn't do that. It's flat everywhere, flat on every torus fiber. So the semi-flat can't possibly be the exact metric, but the statement is that it's actually very, very close to being the exact metric, in the sense that you're exponentially suppressed. The difference between that and the actual metric is supposed to be exponentially suppressed as you suppressed by the distance from the discriminant locus. What do I mean by that? So this m, this quantity m, is supposed to be the minimum of the z gammas, absolute values of z gammas, for which this omega of gamma is not equal to 0. And as you go away from the discriminant locus, these z gammas get bigger and bigger. And so you're getting, in this sense, you're supposed to get exponentially close to the to this very simple kind of semi-flat metric. And this is very similar to a picture of that Gross and Wilson had for K3. So just to say it in words, so as we go far from the discriminant locus, the metric goes like the semi-flat metric, kind of exponentially fast. And so I want to say, yeah, this is a lot like what Gross and Wilson said about K3. Okay. Okay, now I've said as much as I want to say about the kind of general machine here. And now I want to say how you're supposed to apply it in the case of moduli spaces of Higgs bundles. So now I have to give you all of this input data. I have to give it to you in a more explicit way if my goal is to construct the explicit moduli space of Higgs bundles. Okay, so number 2, Higgs bundles. Okay, so suppose C is a compact Riemann surface. And G is a compact Lie group. It's going to be SU2 in most of the examples. So, so what's a G Higgs bundle? So over C. It's first of all a holomorphic GC bundle, E over C. And then a Higgs field. So the Higgs field is like a matrix valued endomorphism of your bundle, except twisted by the canonical bundle. So I mean, so in local coordinates, it's really like a matrix of one forms is how you should think of it, like a matrix of one forms that vary holomorphically. Okay. So there's a moduli space of these objects, these Higgs bundles, which I'll call M check, MH of G and C. So it's the moduli space of semi-stable G Higgs bundles. Or I guess maybe you call that GC Higgs bundles. So very loosely, this is like it's kind of like the cotangent bundle to the usual moduli space of holomorphic bundles. But it's not exactly that. But as a first approximation, it's kind of like that. And now this moduli space, the sort of beautiful fact about this moduli space is that it is a hyperkähler space. So the theorem, which various parts of it were proved by various people. So this whole story was introduced by Hitching, and he proved these things in some special cases. But then to get the general story, you have to combine work of Hitching, Simpson, Donaldson, Corlett. So we're going to construct a hyperkähler metric on this space. The way you do it is by solving some PDEs. So let me write for you the PDE that has to be solved. So someone gives you one of these Higgs bundles. I'll call it E comma phi. in M check. The theorem is there exists a unique Hermitian metric H in E. If the group is G is like UN, then I literally mean a Hermitian metric. Think of E as literally a vector bundle, and we're literally talking about a Hermitian metric in that vector bundle. And otherwise, I guess it's something slightly more abstract. So let's just think of the case of SUN. It's literally a Hermitian metric in a vector bundle. And the statement is this unique one obeying an equation, kind of funny looking equation, which says that the curvature, not that the curvature is 0, but that the curvature is equal to the bracket of phi and phi dagger, minus the bracket of phi and phi dagger. Well, curvature of what? The curvature of the Chern connection. So if you have a metric on the bundle, it's a holomorphic bundle, it has this canonical Chern connection. So you can ask, what's its curvature? So this is kind of like the Narasimhan-Seshadri theorem that says if you have a stable bundle, you can find a metric where the curvature of the Chern connection is 0, right? You identify bundles with flat unitary connections. This is a kind of elaboration of that where we don't look for the curvature to be 0, but we look for it to obey this equation. Okay, so all we have to take from that right now is that you start out with these holomorphic objects, and then they actually have a totally canonical metric structure. And then using that, you can define an L2 metric on the moduli space. So because you have metrics in the bundles, you can define an L2 metric in the moduli space. So I'll call it GL2. So that's a metric on MH. And then the sort of amazing fact is that that metric is actually a hyperkähler metric. Okay, it's a hyperkähler metric. On the other hand, it's kind of hard to say anything explicit about because it's defined using the solutions of this equation I've written in purple, the Hitching equation, which is, you know, some nonlinear system of PDE. So you know that there's this hyperkähler metric, but everything goes through this nonlinear system of PDE. And so at first, it's hard to say anything kind of concrete about that metric. Okay, so we want to study this space. So we want to study M, which will be moduli of Higgs bundles for, I guess, dual group G check, using this Riemann-Hilbert method. And let me right away specialize to the case where G is SU2 and G check is PSU2. Okay, so I want to construct the metric on the moduli of, you know, PSU2 bundles. So I just told you there's a hyperkähler metric, and now I want to construct that hyperkähler metric using this construction that I told you before. So that means I have to give you the data. I have to give you my data A and B. So first of all, datum A was a complex integrable system. Well, sure enough, M check is a complex integrable system. So in other words, as a holomorphic symplectic space, it's fibered over a base of half the dimension. In this case, the base is very simple to describe. It's just a space of holomorphic quadratic differentials on the Riemann surface. Remember, I fixed the Riemann surface at the beginning of this. You just look at the space of holomorphic quadratic differentials on that Riemann surface. That's a vector space, and that's going to be the base of this integral system. So concretely, if someone gives me a Higgs bundle, I map it to a specific quadratic differential, which is minus a half the trace of phi squared. So phi is like a matrix of one forms. If I take the trace of phi squared, that'll be like the square of a one form, which is a quadratic differential. And because phi is holomorphic, that differential will be a holomorphic differential. Okay, so in that way, this moduli space of Higgs bundles gets mapped to a base, and that turns out to be have all the structure of a complex integrable system. I'm going to have to say I need to know what this local system of lattices is in a concrete way. Those were like the homology of the fibers. So I have to say a word about what the fibers are. So the fibers of this integrable system. So those are described in terms of the spectral curve. So given a point phi 2 of this base, you can make the spectral curve, which is just given by this equation. So that's a subspace of the cotangent bundle of C, cotangent bundle of my Riemann surface. It's a 2-to-1 covering of C, which it's just, the two sheets are just the two square roots of the quadratic differential. Or said otherwise, they're the two eigenvalues of this matrix, which is the Higgs field. So if I would draw kind of a cartoon picture of it, something like this. So here's sigma, here's C. It's a double cover, but branched double cover, branched over the zeros of phi 2, zeros of the quadratic differential.
Andy, so Claude Lebrun has a question about, could you clarify the difference between M and M check in this example?
I mean, they're virtually the same, right? One of them is just a quotient of the other. So that the PSU2 space is a quotient of the SU2 space by, you know, the homology of C with coefficients in Z2. So, I mean, the metrics are essentially, even the hypercount metrics are essentially the same. It's just one of them is this discrete quotient of the other one by a group of isometries. I didn't really want to emphasize this difference. I also didn't want to say something which was different from what I said before. Maybe I should have talked about U2 instead. If I talked about U2, then the difference between G and G check would be gone. But then I would have other small problems. Anyway, does that help?
So it wasn't me, it was Claude that asked. I don't know if Claude wants to say.
Yes.
Yeah, I was hoping he would say with it. Okay, maybe I'll go on.
Yes,
On the whole
thank you. That helped.
Okay, good. Okay, so my local system of lattices now. Let me describe its fiber over a particular phi 2. That's going to be the homology of the spectral curve, the first homology of the spectral curve. Except that because of this difference between SU2 and U2, actually don't take the whole homology, I take only the part that's odd under the involution that exchanges the two sheets. So some natural subspace of the homology. Okay, so anyway, so as part of our data, we needed a complex integrable system, and we have one. Now, the second thing we needed are these integers. So what I called the DT type or BPS invariants. So here they're going to be, these are going to be invariants which are literally counting some pretty concrete geometric objects. So one way to describe them is, so given a particular point of the base, a holomorphic quadratic differential, we have, if you just take the absolute value of that quadratic differential, that is a flat metric on C. Okay, so of course C can't have a flat metric everywhere. So the real story is that it's a flat metric except it has singularities at the zeros of phi 2. So singular at the branch points, but everywhere away from the branch points, this is literally a flat metric on C. And now what we do is we consider finite length geodesics in this metric. By finite length, I mean it's inextendable. I don't mean just some arc. I mean finite length geodesics which can't be extended. So each one of these has an associated class in this homology, which I remind you, so it's H1. So let me draw a picture of what those finite length geodesics might look like. So there's two things that can happen. One thing that can happen, so here's our double cover again. So one thing that could happen is we could have two zeros of the quadratic differential. And we could just have a geodesic that goes from one to the other, just goes from one straight into the other. So that's called a saddle connection. And if I have one of those, I can make a corresponding homology class on the double cover just by lifting it up like this. There's some rule for how to orient it. So given a saddle connection, I naturally get the homology class up on the cover. And the other thing that could happen is you could have a trajectory that's finite length just because it's a loop. And if you have one of those, well, those actually come in one parameter families. If you have one of them, there's actually a whole ring that's kind of foliated by them. So we'll call that a ring domain. And then again, given one of those ring domains, you take any member of any one ring inside of there, and you can lift it up to the double cover. Just take both lifts and take them with opposite orientations. So either way, what we're doing is we're studying these finite length geodesics on the surface. To each one of them, we're associating something that keeps track of kind of where it is on the surface, this homology class. And then now we define a number that counts them. So by definition, the number omega of gamma will be the number of saddle connections with class gamma minus 2 times the number of ring domains with class gamma. So that rule looks a little weird, I guess, but that's just the rule. So saddle connections minus 2 times ring domains. Okay, so I was supposed to give you an integrable system and a bunch of numbers obeying this Kontsevich-Soibelman wall crossing formula and obeying some local conditions around the singularities. And now I gave you an integrable system, and now I just tell you that these omega of gamma indeed obey those conditions. And it wouldn't have been true if I'd taken any other combination rather than this 1 and minus 2. So that's somehow why I have to do it. Okay. So now you can formulate a conjecture. The conjecture is that the metric, the L2 metric that comes from the work of, I think in this particular case, it's defined by Hitching. That L2 metric is equal to the metric that comes from the Riemann-Hilbert construction that I described at the beginning. Okay, so in a second, I'll say what's some of the evidence in favor of this conjecture. Let me just remark that even though I told you about SU2, it's not supposed to be limited to SU2. So there's a very similar story for SUN. The big problem for SUN is, so you have an integrable system virtually the same way. You just have an n-fold cover instead of a double cover. But what's tricky is the definition of these integers, these invariants. So here there has to be a much more elaborate definition of omega of gamma. The kind of objects that have to appear. So before there was just one metric on the surface and you studied geodesics. Now you have to consider a bunch of different metrics, and you have to consider kind of trees where different legs of the tree are geodesics in different metrics. And then you have to consider even kind of sicker kind of things like, something like this. And so on. So there's there's an infinite number of topologies that now can contribute. For each one of them, you've got to decide how you're going to count it. And so in a paper with Gaiazzo and Moore, we wrote down a kind of algorithm which if you give me any particular picture of this kind, this algorithm is supposed to produce the corresponding omegas. But it's a much, much more elaborate thing. In particular, these objects are relatively little studied objects, whereas for saddle connections and ring domains, a lot is already known about them. There's a whole book by Strebel on trajectories of quadratic differentials. And yeah, so there's a lot of work on those objects, and for that reason, I think the picture is much better developed in that case. It's not supposed to be limited only to that case. Okay. Okay, so now, let me say a little bit about what's actually known.
Andy, could I
yeah.
insert a comment?
Yeah.
You've chosen what's physically the most difficult case where there are no punctures.
Absolutely, physically the most difficult case. But the theorems,
the spectrum of BPS states is going to be very, very tough to get.
Absolutely. Okay, so Greg's making a good point. Let me say it in the language of this construction. In writing this integral equation, I have a sum over the lattice, this lattice of sort of potential charges. And in the example of it, I'm taking of just a surface with no punctures or anything, homomorphic quadratic differential. This sum is always going to be an infinite sum. So it's not only an integral equation, it's an integral equation which involves a sum of infinitely many integrals. That looks bad. Nevertheless, the theorems that have been proved about asymptotics are proved in that case. They're not proved in the other case. And formally,
so you have to bound how the omegas are growing.
If you wanted to try to prove that our method works in this situation, you would have to have some bounds on how fast the omegas grow. Fortunately, those bounds exist. I mean, like I said, this is a well mathematically studied thing. People have studied exactly that question, how fast they grow. And they don't grow too fast, so it'll probably be okay. Okay, I'll come back to this at the very end if I have time, which I'm a little worried about.
I know you're short on time, but there's you might want to say something about the relation of the BPS states to the special Lagrangian manifolds, especially for this audience.
Yeah, okay, so, right. Yeah, so these pictures, another way of thinking about these pictures is that they're kind of tropical pictures of special Lagrangians. So this omega gamma should also be understood as a count, but a count of different objects. Of special Lagrangian disks. Sorry, special Lagrangian, not only disks, special Lagrangian chains with boundary on this spectral curve sigma. So sigma goes to C. So I drew this picture of a saddle connection. You might have thought of that as a kind of the projection of some disk sitting here. And the boundary of that disk is this cycle that I was calling gamma. To make this precise is a little bit delicate because, of course, I'm drawing this picture inside the cotangent bundle of C. Cotangent bundle of C is not a hyperkähler space. So what do I even mean by special Lagrangian, right? It's not Calabi-Yau. So there's some sense in which it's almost special Lagrangian, and you have to understand this in that kind of formal sense. But morally, it's absolutely the right picture. That's what you wanted me to say, right, Greg?
Yes, exactly. Thank you.
Okay. Okay, good. So let me say just a little bit about the results. So the theorems that exist are about asymptotics. So I wrote for you a kind of asymptotic prediction that would come from this integral equation business. So the asymptotic prediction was that this G Riemann-Hilbert is equal to some simple semi-flat metric plus corrections of order e to the minus 2m, where m now, very concretely, m is 2 times the length of the shortest saddle connection. Or I guess a ring domain, but I think it's always going to be a saddle connection. Now, so that's the prediction, is that the asymptotics of Hitching's metric, so now you can forget all the integral equation stuff if you want. It's just that the prediction would be that when you look at Hitching's metric, you study it very carefully, and you go out to infinity on the base of Hitching's integrable system, what you'll find is that the metric approaches this super simple semi-flat metric up to exponential corrections, and the coefficient of the exponential decay is the length of the shortest saddle connection on the surface. And now, so there's a theorem which is due to the work of various people. So the first by Matteo Swoboda, Weiss, and Witt. Then I contributed some part of it with David Dumas, and Laura Fredrickson contributed part of it. And the theorem is that, sure enough, the L2 metric, Hitching's L2 metric, is equal to the semi-flat plus corrections, but you don't know this exponent 2. So it should be 2 times the length of the saddle connection. And the statement is there's some constant, but it's not necessarily 2. This is in the case, all this is in the case of G equals SU2. Otherwise, there'd be something very similar, except instead of saddle connections, I have to talk about these webs. But the theorem certainly is for, well, that theorem is for SU2. I think I'll skip. I wanted to say something about how this theorem has been proved. Maybe I'll say the very rough idea. Okay, I will say just 1 minute about it. The idea is like this. So here's sigma and here's C. The idea is that this semi-flat metric, you can interpret this semi-flat metric in the following way. You think of it as being the L2 metric, Hitching's L2 metric, but instead of studying Higgs bundles on the surface downstairs, you study Higgs bundles on the surface upstairs. And you study the group U1 instead of SU2. So you can make precise what this means. You study Higgs bundles for the group U1. Now, Higgs bundles for the group U1 are way easier. This nonlinear equation just becomes essentially the Laplace equation. It's like you're doing the ordinary Hodge theory for one forms over the surface. And so in order for this theorem to be true, then what has to happen is that SU2 Higgs bundles on the base are actually very close to being U1 Higgs bundles over the surface, and that's essentially over the spectral curve. And that's the picture that was developed starting by Matteo Swoboda, Weiss, and Witt. Then there's a little more that you have to do in order to get the exponential decay. You have to do something tricky in the regions very near the branch points, but that's somehow the essential idea. So solutions of Hitching equations far out on the Hitching base. The statement is that the solution of Hitching equation when you're far out on the base is very close to being the push forward. So solutions of the SU2 equation on C are very close to the push forward of solutions of the U1 equation from sigma. So that's MSWW's thing. Well, some picture like that is also in the GMN paper, but it was really developed by Matteo Swoboda, Weiss, and Witt. So it's like that, except near the branch points. And so near the branch points, you have to do a little finer analysis, but that's the rough idea. So that's kind of encouraging news from the point of view of this conjecture, because that prediction could have been wrong, but it turns out to be correct. There's a similar thing.
Short on time, so do you have too much more to say? It's just that
I could basically stop. Yeah, so there are a few more theorems along these lines about the asymptotics, which have been proven by various people. There's also, I'll just say, there's also numerical evidence that the full conjecture is true. So I wrote you this complicated thing with integral equations. You can literally solve those integral equations on a computer and compare them directly to the Hitching L2 metric in simple enough examples. And the agreement is very good. So that's some joint work of mine with David Dumas, which should appear soon. Okay, yeah, I think I'll stop there. Thanks, sorry.
Thank you very much. So questions? Greg has a question. If you want to unmute yourself, Greg.
I was having trouble unmuting. Okay, I'm now. I hope you can hear me. Yeah, I would really like to hear Andrew's numerical.
Sure, me too.
Thanks, Greg. Okay, I'll just show you a picture. Okay. So for what's the example? Let me say one sentence about what the example is. The example that I'll show you. Let's take the group to be SU2, the surface to be CP1, the bundle to be the trivial bundle, and the Higgs fields. Let's take some explicit Higgs fields written like this. So here, this C is a complex number which we allow to vary. So we're studying a one-parameter family of Higgs bundles. Now, these are Higgs bundles not of the ordinary kind, because they have a singularity at infinity, so-called wild singularity. I mean, what I'm writing here, thought of it on CP1, right? That phi would have a big singularity at infinity. But there is supposed to be a theory also of Higgs bundles with wild singularity. So this should be thought in every sense as an example of all the same phenomena that I was describing, but it's numerically simpler. So this family of Higgs bundles is sitting inside of a two-dimensional moduli space. This family is a one-dimensional family. It's parameterized just by this C. And so the Hitching metric just looks like this. There's just a function G of C. And in fact, it has rotational invariance. So it only depends on the absolute value of C. And so we calculated that function. So, okay, so now I'll show you the plot. So we calculated that function in two ways. We calculated it on the one hand, numerically, by actually solving Hitchin's equations. In this particular case, Hitchin's equation is some PDE in the plane. You can just solve it numerically. And on the other hand, we solved these integral equations numerically and compared the metrics so that gives you two different formulas for the metric. And yeah, so here's a picture of what those two formulas look like. Okay, so on the left side of the picture is the two metrics. You see there's the plus signs represent the metric computed as an L2 metric using Hitchin's, literally the definition. The crosses computed by this integral equations method. So this is a plot of this is the function G of C, and you see that the pluses and the crosses are like exactly on top of each other. So that's the sense in which there's very good agreement. On the right side is the residual, the difference between the two computations. I can say something about why, but the zeroth order statement is just that a priori these two things would have nothing to do with each other, but in fact they're extremely close. The dashed line is the semi-flat approximation. So you see the semi-flat is very good at large distance. This asymptotic is very good at large distance, and of course it breaks down as you go to small distance. The actual metric is smooth. Okay, maybe that's
great. I see that Simon Donaldson has a question. So you have to unmute yourself, Simon.
Metric, do you get some smooth structure, or do you have to go to do you have to take all the terms to get something smooth?
Well, okay, so it's smooth if you take all the terms. The semi-flat metric is also smooth. Let's see, there's different ways of kind of truncating the thing. So when you say all the terms, what kind of truncation are you thinking of?
Well, I'm not quite, I mean, if
Yes, sir.
Right. Maybe I'm thinking if you took an expansion in terms of your, if you were taking asymptotic expansion, starting.
Oh, yes. Yes,
like,
right. So if you make an asymptotic expansion, you have terms proportional to these omegas, and then you have additional terms that are proportional to products of the omegas, and additional terms that are proportional to, you know, arbitrary combinations of these omegas. And it's true that if you only take the terms, for example, that are linear in omegas, which are the leading terms in an asymptotic expansion in a specific direction, then it will not be smooth. It has kind of Stokes phenomenon as you move around. And the higher terms have to come in just such a way that they cancel the discontinuity in the leading asymptotic. That's essentially how this Kontsevich-Soibelman formula gets into the game. One way to think of the Kontsevich-Soibelman formula is that it's exactly engineered so that the multi-particle terms cancel the discontinuity of the one particle terms.
It is another possibility that you get an asymptotic formula for the L2 metric, but not actually a convergent series. Would that be another weaker
Right.
projection?
So I mean, if we take this integral equation and try to extract an asymptotic expansion from it, so I think you can do that. It hasn't been done completely systematically, although people have written down like the first term beyond the semi-flat. I don't think people have written down systematically the higher order terms. I think that asymptotic expansion would be only an asymptotic expansion. It wouldn't be a convergent series. But on the other hand, the statement is that if you actually go and solve this integral equation, then it produces the actual metric. I mean, that's not a statement about asymptotic expansion. I mean, so
I see.
Yeah.
So Dominic, did you have a question?
Okay, well, can you tell us what's known in the kind of Calabi-Yau-3 case? And you mentioned Donaldson-Thomas invariants and so on. So what can you do for Calabi-Yau-3 folds or three Calabi-Yau categories?
Okay, for constructing metrics on Calabi-Yau-3 folds, basically we can't do anything with this technology. This is really engineered. It's really geared toward the, you know, exploiting this twistorial family. So
I didn't mean that. I meant what can you do with the Donaldson-Thomas invariants of a Calabi-Yau-3 fold?
Oh, of a compact Calabi-Yau-3 fold?
Or a three Calabi-Yau quiver category or whatever.
Okay, good. So this example that I was describing actually is an example of Donaldson-Thomas invariance of an actual Calabi-Yau-3 category, even though I didn't present it that way. So that's a theorem of Bridgeland and Smith, is that exactly the invariance I defined in this case of Hitching system for SU2. They are the DT invariants of some category that they describe. And they give a kind of quiver description of it, but then there's also a paper of Ivan Smith where he describes it as some version of the Fukaya category of a particular non-compact Calabi-Yau, which is like an A1. It's like you take an A1 singularity fibered over the Riemann surface. And that's supposed to work in higher rank too, but in higher rank, I think there are no theorems about that. And even the exact category, I think, hasn't been fully constructed, although there's work of like Hayden, Katsarkov, Kontsevich. I think, so I don't know the exact status of it.
Yeah. I think it's Pandit as well, is it? Is that the one?
Yes, Pandit. Sorry, yes, absolutely. Pranav Pandit. Thank you.
So in general, we're hoping to build a hyperkähler manifold with a complex Lagrangian fibration over the Bridgeland stability.
Right. So there's a tricky thing. There's a tricky thing here. So this space, like the Hitching base that I was using in this construction, that is not the space of Bridgeland stability conditions on this category. It's a kind of half-dimensional slice inside of the space of Bridgeland stability conditions. To get the space of Bridgeland stability conditions in that example, you would have to allow not only vary the quadratic differential, but also allow the base Riemann surface to vary, you know, to move inside of the Teichmuller space. So so Bridgeland's thing, like, you know, the Bridgeland stability conditions in that example is like kind of universal version of the Hitching base. And one of the confusing things about this whole story is, right, if someone gave you just an abstract Calabi-Yau-3 category, how do you identify the kind of slices of it, which are the analogs of the Hitching base? But I think Tom Bridgeland has made some progress on that, actually. But I know for a long time that was a stumbling block.
So Yang Li has a question, which is, could you explain where the integral equation comes from?
Not easily, I'm afraid. I mean, it's engineered to produce all the properties that you need. So the key properties that it has to have are that these functions x gamma, so they're supposed to be like holomorphic Darboux coordinates. What properties do they have to have? Well, first of all, because they're only piecewise smooth, naively there would seem to be a problem. If I'm using them to define a holomorphic symplectic structure, the fact that they're only piecewise smooth looks bad, right? Because you don't want the holomorphic symplectic structure to jump. You want to define a single smooth holomorphic symplectic structure. So one thing about this equation, it's engineered in such a way that the jumps, although they jump by symplectomorphisms, so that the holomorphic symplectic structure is actually the same. The other crucial property they have to have is that they're defined as functions of zeta, where zeta lies in C star, and they have to have good asymptotic behavior as zeta goes to 0 and infinity in order that the kind of structure of twistor space extends over 0 and infinity. You don't want to construct a thing fibered over just C star. That's worthless. You have to get the whole twistor space. So this equation is kind of engineered to have those properties. And in the first paper with Greg and Davide that we wrote about this, we gave I'm not sure now that I'm in a math department, I'm not sure if I would exactly call it a proof, but let's say we gave a proof sketch that the thing really has all the necessary properties. But where it really came from, I wish I could say, oh, it just came from something in physics, but the truth is it came from a combination of many partial things that we knew in various examples, trying to put them together in kind of the simplest possible way that would work. After the fact, it turns out to be related to something in physics called the thermodynamic beta ansatz. But even that relation is not totally understood. So I'm sorry, I can't give a simple answer to this question.
Okay, I think we could stop the formal part of the questions now.